Imagine climbing a ladder, but not just any ladder, a ladder so long it stretches from Earth to the moon. Is such a ladder even possible? How long would it take? And how would gravity change your experience as you climbed? Let's start with the first step, leaving Earth. At the surface, gravity is relentless. Every step feels like you're hauling your full weight against a powerful invisible force pulling you down. As you climb higher, something extraordinary happens. Gravity begins to weaken. For instance, at around 100 kilometers above Earth, you reach the Kármán line, which is often considered the edge of space. Here, gravity is only slightly reduced. It's still about 97% as strong as it is on the surface. You're technically in space, yet Earth's pull remains almost as strong. As you continue to ascend, gravity continues to drop off following the inverse square law. Eventually, you reach a fascinating spot called the Lagrange point, where Earth's and the Moon's gravities cancel each other out. At one of the stable points, L4 or L5, you could let go of the ladder and just float indefinitely, forever caught in a cosmic tug-of-war. Let's keep climbing. Something strange happens as you approach the Moon. It feels like your ladder has flipped upside down, effectively flipping your sense of up and down. If you were to lose your grip here, you wouldn't just float peacefully to the lunar surface. Unlike Earth, the Moon has no atmosphere to slow you down. Without terminal velocity to limit your fall, you'd accelerate all the way, hitting the Moon's surface at thousands of kilometers per hour, even though the Moon's gravity is only about 1/6 of Earth's. Assuming you make it safely to the Moon, the climb down feels much easier. The Moon's gravity is only about 1/6 that of Earth. For example, if you weigh 60 kilograms on Earth, you'd feel roughly like you weigh 10 kilograms on the Moon. Every movement becomes light and effortless, a dream compared to the constant struggle on Earth. Now you might wonder, could a ladder like this really exist? Unfortunately, Earth's gravity makes it impossible. No known material could withstand the immense stress of holding itself up against Earth's pull. On the Moon, though, it's more plausible, thanks to the weaker gravity. Now let's extend our ladder beyond the Moon, heading toward Mars. To get a sense of just how far that is, if you climbed continuously without stopping, at a speed of 3 kilometers per hour, it would take you about 10 to 15 years just to reach the Moon. Now, to continue on to Mars at that same pace, it would take approximately 74.9 million hours. That's about 8,550 years of non-stop climbing. If you were feeling particularly adventurous and decided to keep climbing past Mars to Jupiter, that leg of the journey alone would take roughly 21,050 years. Now, the Sun's magnetic field extends far beyond the planets. If you wanted to reach the edge of this field, a point about 5 times as far from the Sun as Pluto, your climb would take an estimated 600,000 years. But what if you wanted to leave the solar system entirely, escaping the Sun's gravitational pull altogether? Let's say your destination is the Oort cloud, a distant region of icy objects. That final leg of the climb from the edge of the Sun's magnetic field to the Oort cloud would take you only another 570 million years. These numbers are so large they're almost impossible to truly grasp, emphasizing just how vast our solar system is. As you move into interplanetary space, you'll notice another shift. The Sun's gravity takes over. At Earth's distance, the Sun's gravitational pull is just 1,800th of Earth's surface gravity. It's remarkable that this tiny force is strong enough to hold planets as massive as Jupiter in orbit. Yet, as you climb away from the Sun, this pull weakens even further. Paradoxically, escaping the solar system entirely would feel easier than escaping Earth. The Sun's gravity decreases so quickly with distance that by the time you reach the outer planets, it's practically negligible. In fact, if the Sun's gravity were as strong as Earth's surface gravity, the planets wouldn't hold together. They'd disintegrate into rubble, like Saturn's rings. Now, let's tackle a more extreme challenge: climbing toward Jupiter. Imagine you've made it to the Jovian system. Climbing down toward Jupiter's surface, or rather, its dense atmosphere, would be almost impossible. Jupiter's gravity is a crushing 2.5 times that of Earth. If you weigh 60 kilograms on Earth, you'd feel like you weigh 150 kilograms on Jupiter. Even if you had superhuman strength, Jupiter presents other challenges. Its intense radiation belts and crushing atmospheric pressures would make survival unlikely. But for the sake of the thought experiment, let's just focus on the gravity. Climbing out of Jupiter's grip would be one of the hardest physical feats imaginable. One last thing to consider: even in space, a ladder stretching from the Moon to Jupiter couldn't stay perfectly straight. The ladder would collapse under its own gravity, curving into a more spherical shape over time. This thought experiment reveals the incredible power of gravity and how our perception of up and down is just an illusion. Gravity is everywhere, shaping our journey no matter where we climb. As you climb past Jupiter, Saturn, Uranus, and Neptune, the sun's gravitational influence continues to fade, though it still holds sway over the distant Oort cloud, a vast shell of icy objects surrounding the solar system. By this point, the sun would appear as just another star in the sky, its gravity barely perceptible. You'd be entering interstellar space, where the gravitational pull of other stars begins to compete with the sun's influence. And while gravity remains the overarching force shaping your journey, other challenges emerge in interstellar space. The sheer vastness of distances dwarfs anything experienced within our solar system. Within the solar system, most of the harmful space radiation comes from the sun's solar winds and bursts of energetic particles. Thankfully, Earth's magnetic field and atmosphere shield us from much of this radiation. The edge of the solar system is where the sun's magnetic field ends, and you enter interstellar space. And as we move into interstellar space, a new danger emerges. Cosmic radiation made up of high-energy particles originating from supernovae, distant stars, and even black holes. Unlike solar radiation, cosmic radiation is far more intense and pervasive, with particles traveling near the speed of light. Without the sun's magnetic field to deflect some of this radiation, it becomes far more treacherous. In this region, every moment of exposure would bathe you in particles capable of damaging cells at an unprecedented level. The protective shielding required to survive such radiation is far beyond anything we've developed for current spacecraft. Interstellar explorers will need to conquer not just the vast distances between stars, but also the deadly cosmic rays that permeate the space between them. I hope you enjoyed this journey through the solar system. Thanks for watching and have a wonderful day.